Okay, so welcome everybody to the last activity of the QFT and geometry seminar series for this year. So
actually not true. There's one more next week.
Next week.
Yeah.
Oh, yes, you are right. Almost last activity. Sorry. Yes. Almost last activity of this seminar series for this weird year. So we are ending this year, almost ending this year with this more festive activity of having a workshop, mini workshop with 12 excellent speakers. And I would like to thank all the speakers who agreed to talk on a very short notice. So here you can find on the website the schedule for the talks. I just want to let you know that tomorrow's lectures are shifted. The second bunch of lectures was shifted by 1 hour relative to today. So pay attention for this tomorrow. So each talk will be half an hour, so a little bit less, hopefully. And I will ask you to refrain from asking questions during the talks and ask the questions at the end of each talk, or type it in the chat, and then we will I will ask the speaker in the end of the talk. So let me stop sharing my screen. So Evyatar, please share your screen.
Okay, I'll share my screen.
Okay, so the first talk will be given by Evyatar Sabag.
Wait 1 second. Yes.
Can you just make it full screen? Or?
Yeah, for some reason when I make full screen, I can't see the people. Well,
we are not
okay.
important.
Yeah, I guess.
Okay.
Okay.
So the first lecture is by Evyatar Sabag, and he will tell us something about 4D Lagrangians from 6D RG flows.
Okay, so thank you, and I would like to thank the organizers for giving me the opportunity to speak on this mini workshop. My name is Evyatar Sabag, and I'm on my last year as a PhD student at Technion under Shlomo Razamat. And I'm going to talk about 4D Lagrangians from 6D RG flows based on a series of papers given here with my collaborators Shlomo Razamat and Gabi Tzafoyot. Okay, so the goal will be to find 4D Lagrangian descriptions for 4D quantum field theories obtained by compactifying 6D SCFTs on a Riemann surface. So I'll start with a short background where first I'll introduce how we compactify from 6D to 4D. So one can generate classes of 4D n=1 SCFTs by compactifying 6D 1,0 SCFTs on a Riemann surface. And there are several options. So you can compactify on a closed Riemann surface. One can give fluxes to U1 subgroups of the 6D global symmetry. And one can also compactify on Riemann surfaces with punctures with associated symmetry. So the 6D 1,0 SCFTs we'll focus on are the ones described by NM5 brains probing in ADE singularity, where these were introduced in this paper. And specifically, I'll focus on the A and D type, where the A type or the ZK singularity on the tensor branch is described by this quiver with 2 SUK global symmetries and another U1 symmetry where the half hypers is charged under. We have n-1 SUK gauge nodes and half hypers in the bifundamental of the two nodes. In the D type or DP+3 singularity case, the tensor branch is described by a quiver with 2 SO 2P+6 global symmetries and 2n-1 such gauge with the USP and SO interchanged. And in between, there are half hypers in the bifundamental as well. And now, the first thing we want to do or look at is flows between ZK singularity and a ZK-1 singularity. Okay? And we can generate such flows by giving a vev to an operator which we call the end-to-end operator. And this is because it winds from one end of the quiver to the other, and it's in the bifundamental of the two SUKs. And by giving this web, we can flow to a similar 6D theory, only with the singularity reduced to k-1. So next, what we want to do is compactify these two theories on a general Riemann surface with some fluxes. And once we do that, we reach what's called the classes K, which was denoted by Evyatar and Rosamat. And of course, in the case of k-1 singularity, we get to classes k-1 theory. And next, what we want to do is look at a 4D operator, which is the corresponding one to the 6D operator, which we gave Vev to. And it corresponds in a manner such that it is charged under the same abelian subgroup of the 6D global symmetry. When remember, in general, the 6D global symmetry is broken into U1s by the fluxes. Okay, so we want to look at Vevs for this operator here in 4D. And this operator leads us to another classes k-1 theory. And the question is, can we find this process of compactifying and giving a Vev, or giving a Vev and then compactifying, can we find two theories which are the same theory under some mapping? So in order to look at that, we'll first examine a simple case of k equal 2 and n equal 2. And in this case, we'll have an SU2 beta and SU2 gamma symmetries here. And what we'll look at is we'll look at a torus compactification, where we give flux to the U1 beta abelian part of the SU2 beta. And this theory was described in this paper, and it's given by this quiver here, where we have two SU2 gauge symmetries and some fields, and the x's denote flipping fields. And in this convention, we use the super conformal index convention, where the charges of the field are denoted by fugacities, where the power of the fugacity gives us the charge under the corresponding U1 symmetry. In addition, we have here PQ, where the power of PQ is half the R charge of the field, where the R symmetry we chose here is the one inherited from 6D. And now what we want to do is, again, generate a flow by giving a Vev to the end-to-end operator that we talked about earlier, the 4D one. And in this case, this is the baryonic operator appearing here in green. So this Vev forces us to break the U1 beta and U1 gamma to some diagonal U1, which we call U1 epsilon, and also to set the fugacities in some manner. Once we do that, we flow to a new theory, which is the one described here, where we have an SU2 with 3 adjoints and extra singlets with charges square root of t and epsilon +1 and -1. And this theory can be described by in Evyatar's class S as a torus with 1 puncture. Okay, so basically we started with a torus with no puncture and some flux. We gave a Vev, and we've ended up with a torus with flux and an additional puncture. And what we see is that this is actually quite general. And for any n and k, such processes can happen where we get additional minimal punctures. And another thing is that here, basically, we have the Lagrangian of both sides. We know the initial Lagrangian, and we can identify the end Lagrangian. And in class SK, there are many such Lagrangians, and we can actually generate a mapping and see how these theories flow when we give this Vev. And what we find is a 4D constant Vev that can lower k and adds minimal punctures, which are numerated by this number here, which is the flux under the end-to-end operator. And this is just the sum over the fluxes times the charge of the end-to-end operator under the same U1 as the flux. And this gives me the number of extra minimal punctures that I'll get under this flow. Okay. So now going back to the what we saw in with the 6D VEV. So when we compactify with flux, a constant 6D VEV is not in general a vacuum solution. Thus, we expect the 6D VEV to be space dependent when the flux to the end-to-end operator is non-vanishing. And what we see from our analysis before is when taking the Riemann surface to be small, the space-dependent VEV appears as additional minimal punctures on the surface. And here again, we have the picture where we started with. We have the initial theory A in 6D. We turn on, we put it on a Riemann surface with fluxes, and we also turn on a VEV. And apparently, the fluxes determine in some cases that the VEV cannot be constant and have to be space dependent. And once we compactify, this space dependence can appear as minimal punctures on the Riemann surface. On the other end, what we saw is that we basically have a VEV that we can give to an operator in 4D and flow to another 4D theory with additional minimal punctures. So that's what we saw in classes K. And now what we want to do is do the same process in D-type, where again, we will have the initial theory, but at the end result, we want to find something new. So D-type 1,0 6D SCFTs have similar end-to-end operators. And the question is, will giving a VEV to these operators generate extra minimal punctures? And here we see the operators. Again, these are the ones winding from one end to the other. Okay, so for D-type, flux tubes and tori compactifications have known Lagrangians, and one can call it classes D. And these were found by these papers. And what we find is compactifications with extra minimal punctures by setting the VEV to the end-to-end operator. And here I'll give some examples of theories. So one example I'll give is the n=1 D5 flux tube, where this is the matching quiver. And also the n=1 D4, which is also the rank 1 E string flux tube with this quiver. And the reason I give these quivers is that the next thing we'll do is look at an example of a flow between n=1 D5 and n=1 D4, or rank 1 E string, and we will use these flux tubes. So our next example is really to look at this torus theory, which is combined of several such flux tubes as we saw before. And again, we want to do the same process, give a VEV to the end-to-end operator, which here is the baryonic operator appearing here in green. This again sets the fugacities in some manner, and we end up with this theory, which we expect is to be a torus with an extra puncture in E string. Okay, so now what we want to do is analyze this result, and we can use Sabag dualities to massage it a bit from this form to this one, where in this form we can identify the theory as two flux tubes and the trinion glued together, where these are the flux tubes that I showed before. And next we're going to analyze this trinion and show its properties and what it holds. Now, before we go to analyze the trinion, I want to first give some notes on D-type maximal punctures. So when compactifying 1,0 6D SCFT in general on a circle with certain choices of holonomies, one may find effective 5D n=1 gauge theory descriptions. Different choices of holonomies give different 5D theories, and the puncture symmetry matches the 5D gauge symmetry. And in the general case of general N and P, there is at least one known such 5D theory that was found here. And this one gives me a maximal puncture with the following symmetry of SUN to the 4 times SU2N to the power P. Now, in the specific case of n equal 1, there were found several other 5D gauge theories in these papers, and these give me some extra punctures with symmetries SUP plus 1, USP2P, and SU2P, which is the reduction of the one that we had in the general case. Now, in our case, we looked at basically our end result is that with P equal 1. So if I put here P equal 1, what I see is that I get that all these punctures are actually SU2 punctures, and there is one type of puncture. So now let's go back and analyze our result further. So here is the result that we found before. And this is the E-string trinion, three punctured sphere. And it has two SU2 maximal punctures, which can be shown here, the one in green and the one in red. And an additional U1 puncture appearing here in blue. But this puncture gets enhanced to SU2 in the IR. And this can be seen using the superconformal index, where the fugacities of epsilon generate irreducible representations of SU2. So basically, we get this picture here with 3 SU2 punctures. And we observe that the new SU2 puncture is a maximal puncture. And this has the following evidence. First, Tuft anomalies match to other maximal punctures, as we expect. Anomalies allowed to gauge the SU2 when gluing two such punctures. Obviously, such gluings are non-Lagrangian, as these SU2s only appear in the IR and we don't see them in the UV. And finally, gluing several such trinions to a genus G surface, anomalies match expectations from 60, and the superconformal index is as expected. And here I show an example of a superconformal index of a genus G surface with no fluxes. So here we get in order PQ the number of flat connections plus complex structure moduli. And we see the 248 representation of E8, where E8 is the global symmetry of the 6D SCFT, which is the rank 1 E-string. Okay. So we had before the trinion, and this trinion did not exhibit the E8 global symmetry. But we did have 2 SU4 symmetries and 2 U1 symmetries, and these combine to create these E8 representations under the following branching rules appearing here. Okay, so now going back to the more general case, and we see that it works in the same way. So for general N and P, what we can do is again set the end-to-end operator VEV on a torus, and this lowers P and adds minimal punctures. Once we get that, we can then extract the trinion by cutting the torus. Okay, so in the general case, again, we'll get such a case after the flow where we have a torus with one minimal puncture. Next, by using our knowledge on maximal punctures and how we can glue them, we can cut it and find the following trinions. Where in the general case, one finds a trinion with 2 SUN to the 4 times SU2n to the P maximal punctures, and 1 minimal puncture of symmetry U1, which does not get enhanced to SU2 in the general case. But when we look at N equal 1, what we see is we get we get several such trinions. And in what we found in examples is the SU2 to the P1 and SUP plus 1, where in both cases, the minimal puncture has a symmetry of SU2. Now, specifically looking at the SUP plus 1 trinion, it has an extremely simple form, which is given here. And we can see here the SUP plus 1 symmetry of one puncture, the SUP plus 1 symmetry of the other, and the SU2 symmetry of the minimal puncture. So in this case, the SU2 is not only apparent in the IR, it's apparent in the UV. And we can, and it's completely Lagrangian. And if we take P to equal 1 and go back to the E-string case, we basically find a trinion with 3 SU2 punctures, which are all apparent in the UV. And we can use them to generate any Riemann surface that we want with completely Lagrangian gluings. okay, on Lagrangian theories. Okay. So finally, I would like to go briefly over another observation that we had in the minimal n equal 1 classes D. So in this case, we saw that P minimal SU2 punctures combine to a USP to P maximal puncture in the IR. Okay, so basically what we can do is take, let's say, P of these trinions that we found before, glue them together, and now we have a Riemann surface with P minimal punctures. And what we see is that these punctures combine to create a third maximal puncture of symmetry USP to P. So here, basically, we find a trinion with 3 maximal punctures. Similar phenomena were found also in these papers. And now what we can do is, well, first we want to show evidence that indeed this happens. And indeed, we find the same evidence as we found before for the symmetry enhancement. So 't-Hooft anomalies match USP to P punctures. The index minimal puncture symmetries form irreducible representations of USP to P. And anomalies allowed to gauge the USP to P when gluing 2 such punctures. And in addition, gluing several such trinions to a genus G surface, anomalies match expectations from 60, and the superconformal index is as expected. And finally, I can show the superconformal index of a genus G surface with no fluxes. And again, we see the familiar form from before, where here we get the adjoint of SO4P plus 12, where SO4P plus 12 is the global symmetry of the 6D SCFT. Okay, so basically we have shown that in this symmetry, these minimal punctures actually get enhanced to a maximal puncture. And now we have a trinion with 3 maximal punctures, and we can basically generate any compactification of minimal classes D that we want, and have a Lagrangian for it using these models. Okay, so I'll summarize. So what we found, one can map classes K compactifications to classes K minus 1 by using the Vev to the end-to-end operator, and minimal punctures can be added. So that's what we first found. A similar mapping exists for D-type compactifications and allow finding trinions with 2 maximal punctures and 1 minimal puncture. For the special case of n equal 1, dp plus 3 type compactifications, we see that p minimal punctures combine to maximal USP to p punctures. And once we have this, we can construct 4D Lagrangians for all the compactifications of n equal 1 D-type. In addition, I did not show it, but this also happens in a similar manner for n equal 2 A-type, where n again is the number of M5 rings probing the singularity. And I did not show it due to lack of time. And finally, these infinite classes of theories enjoy generalized S-duality exchanging punctures of the same type. We find symmetry enhancement and gauging of enhanced symmetries. And finally, I will leave you with this outlook of future questions. Okay, thank you.
Thank you very much, Evyatar, for the talk. So any questions?
I have one. So the operator that you use in 6D to flow to the Riemann surface with a flux, the operator that depends on the Riemann surface. So the gradient should give you some sort of scale, which somehow is dialed. By the time you get to 4D, it blows up, and then you can localize the flux at a point. Do you understand what operator you should associate to that?
All right, so let's go back. So again, here in the beginning of this picture, you want an operator again that does what?
So you said that this operator O6D depends on the Riemann surface itself, right? It depends where you are on the Riemann surface.
Okay, it's a space dependent.
Yes. So then and then somehow by the time you get to 4D, it leads to a localized puncture. So somehow this operator sort of collects all of the flux and localizes it to a point. So if you then look at the gradient of that operator on the Riemann surface, that should be associated to a different operator, maybe some marginal coupling or something like that. Do you understand what that is?
I think, okay, so what we looked at are only such operators or flux that is localized and looks like a series of delta functions. Okay, so it's localizing on a point on the Riemann surface. And thus this operator, actually we only looked at operators that are constant up to some points where they jump. Okay, so regarding other operators, I don't know, if, not that I know of in this case.
So the 6D thing that you get is actually not a smooth thing over the Riemann surface. That's what you're saying.
It's a smooth thing up to some singular points. If I understand you correctly.
Okay, thank you.
Okay.
Craig, Laurie had a question.
Hi, yes, I have a question. So I wanted to make sure that I understand how much supersymmetry you have correctly. So you have an example in a couple of slides where you do the T2 compactification. The first one, it was fairly soon. Yeah, I think it's here. So here on the right-hand side, you have the classic class S, meaning n equals 2. Is that right?
Yeah, where in this case, you can also call it n equal 2 star, I think.
And on the left, you also have n equals 2.
On the left, I have n equal 1.
So do you see this kind of enhancement of n equals 2 to n equals 1 often in these examples that you looked at for various values of n and k?
Okay, so this only happens in this kind of simple cases where I look at k equal 2, and then I flow basically to k equal 1, which is no singularity. In the general case, no, I get some singularity, and this also has an n equal 1. So in the general case, this is an n equal 1 mapping.
I see. So there are these examples where if you take the you take arbitrary n for the D series, and then you just compactify it on a T2 with no fluxes or anything, and you get like an n punctured sphere with, I think, 2 maximal and n simple or something. This is not your example. This is something else. But I was just curious because in that case you have n equals 2.
Again, so what's the example? I'm sorry, I didn't understand.
So if you take the D series for arbitrary n, when you compactify it on a torus with no flux or anything, you get n equals 2 theory.
Yeah.
Supersymmetry, n equals 2 theory, with it's a sphere with, I think, it's roughly n simple punctures and 2 maximal punctures. So you don't see sort of any Lagrangians for these types of theories?
Not that we looked at.
Okay. Okay, thank you.
Okay, thank you.
Any more urgent questions? Okay, if not, let's thank Evyatar again. And please, Evyatar, stop sharing the screen. Yes, okay. So Chris, you are next. Okay, so next speaker is Christopher Couzins, and he will tell us about rotating black holes, something about rotating black holes and near horizons in M theory. Okay, take it away. You are muted, Chris, so unmute yourself.
Oh, sorry. So I'd like to thank the speakers for letting me speak today. And as Shlomo said, I'm going to be talking about near horizons of rotating black holes, and we're going to talk about them when they're embedded in 11D supergravity. So this is recent work with 3 PhD students in Utrecht. So we have Eric Marcus, Koen Snellendink, and Damian van der Heester, whose names I have very much butchered because I do not speak Dutch very well. So I'll quickly give an outline of what we want to do. So I'll begin with some usual spiel about the latest in ADS black holes. And I'll quickly review something called GK geometries, which I'll try to explain why these are relevant for near horizon geometries. I'll then move on to explaining a bit about rotating black hole near horizons. This is more of a review. And then in section 4, I will start talking about some of the work in our paper, and I'll try and conclude with some wrapping up what we've done, and then maybe some wild speculations at the end. Okay, so I don't think I need to explain to anyone what a black hole is, but I thought something interesting was that the first notion of a black hole was actually thought about in 1784. And it's 250 years later, they're still kind of curious to us. So I think one of the most important results that we have is Bekenstein and Hawking in the 1970s, where they showed that black holes obey some form of thermodynamic laws, and that in particular that you have this formula here, which gives you the leading order contribution to the entropy. So here A is just the area of the horizon, and G is just Newton's constant. So there's 2 things that are very interesting about this. Firstly, if you did just normal thermodynamics, you'd expect an entropy to scale as the volume, whereas here it scales as an area. So you should really think holography. And the second thing is, if you really wanted to take this idea of black hole thermodynamics to the extremum, you'd say, okay, statistical mechanics says I should be able to compute some microstates for this, which precisely gives for me the entropy of this black hole. So for asymptotically flat black holes, Strominger and Evyatar in 1996 did such a microscopic analysis, and they give a description of the microstates of this class of black holes purely by looking at string theory. You have certain brane constructions, and from these brane constructions, you basically compute the microstates of this black hole from a field theory analysis, essentially. It was 20 years later that ADS black holes had their first accounting of microstates, and this was by Benini, Christoph, and Alberto, who's in the audience, I believe. So I want to quickly explain what happens in this in Alberto's paper. So roughly, there are 2 perspectives you can take. You could take a UV approach, or you could take an IR approach. So in their paper, they look at asymptotically ADS4 black holes with magnetic charges. And since it's asymptotically ADS4, you'd say, okay, there's some dual CFT living on the boundary of ADS4, so you have some 3D CFT. And to count the microstates of this black hole, we can count the microstates in this. We just need to evaluate certain operators in this CFT. So the relevant thing to compute is the partition function of this 3D SCFT placed on the boundary of ADS4. So you can use SUSY. The key part of this is that you can now use SUSY localization to actually evaluate this partition function. This was, I think, one of the things that was missing for doing this earlier. So this you can then enumerate the microstates of the black hole by looking at this partition function. So having done SUSY localization, you've reduced the infinite integral down to a finite integral. And if you want to make a bit more progress, you can assume that the black hole the charges of the black hole are large. And then you can do a saddle point approximation for this for the partition function, and from this you can extract out the entropy. So one key point that I want to emphasize is that the saddle point approximation is precisely just an extremal problem. You're extremizing something, finding the minimum, and then evaluating it at this minimum. So the entropy of the black hole is given by some extremal problem. So the second approach is to look at the IR. So for a static black hole, the near horizon of the black hole is ADS2. So ADS-CFT says there should be some 1D quantum mechanical theory living on the boundary, essentially. And this should then describe the degrees of freedom of the near horizon, and therefore also the black hole. So you can view this as an RG flow across dimensions from this 3D SCFT down to a 1D superconformal quantum mechanics theory. So roughly what you want to do is you take this 3D CFT, you compactify it on some geometry. In this case, it will be a Riemann surface, and this will give you precisely the quantum mechanics theory. So now again, you want to try and evaluate some partition function. In this case, it's just going to be the Witten index. And to do this, you use something called I-extremization, which computes this partition function essentially in the same way that F maximization computes the sphere partition function in 3D. So you extremize over all the choices of possible R symmetries, and the one that extremizes the index is precisely the exact R symmetry in the IR. So this is analogous to F maximization, and also in spirit to A maximization and C extremization in 4 and 2 dimensions. So the key point again is that there's some extremal problem in the field theory that computes the entropies of these black holes. So if you take holography to, if you really believe in holography, you'd say, okay, there must be some dual geometric extremal problem that I have. So Sen's quantum entropy functional, or the extraction mechanism, is an example of this. You extremize some functional for a set of scalars, and on the horizon, the extremal value gives you precisely the scalars on the horizon. And from this, you can compute the entropy. A similar idea, not quite similar idea, but a similar geometric problem is that something called volume maximization, which was by these people here, which computes the volume of Sasaki-Einstein manifolds. And this is related to the A central charge of 4D SCFTs, or 3D if you're in the 7D Sasaki-Einstein. And this gives you the dual of A maximization. Even more recently, along with Jerome Gauntlet, Dario Martelli, and James Sparks, we came up with a geometric dual of C and I extremization. So this is, we looked at a particular class of theories, which in geometry are ADS3 solutions in type 2b, which can be seen as arising from wrapped D3 branes, and ADS2 solutions in 11D, which come from wrapped M2 branes. So one of the realizations is that this ADS3 is precisely the near horizon you'd get from a static black string, whereas ADS2 is precisely the near horizon you'd get from a static black hole. So I've given talks on this, which took an hour, but I'll try and summarize this paper in one slide. So the rough idea is that the geometries of these solutions are precisely to have this form of internal metric. So n is equal to 3 for type 2b and 4 for 11d. So you have this one form here, beta, which is known as an R symmetry vector. You have this base here, which is a scalar, and you have this scalar here, which is determined by the Ricci scalar of this base. So this looks very much like Sasaki-Einstein geometry, and it has some close parallels, but it's not quite. So this geometry is also supported by a two-form flux, which is completely explicitly written. And these two-form flux, if you wedge it with the three-form of the volume of ADS3, you get the part of the five-form flux in type 2b. And if you wedge it with ADS2 in 11D, you get the electric part of the four-form flux. So this geometry is completely determined by this master equation here, and supersymmetry fixes for you this eta b and the flux F. So to have a solution, all you need to do is solve this nasty looking equation for a Laplacian on the Ricci scalar of the base. So this was work by Jerome, Nakru, Kim, and Park up to this point. And then the content of the paper from 2 years ago and some other papers by other people was that you could compute this quantity here at the bottom without needing to know the explicit metric. So you don't need to solve this for a metric. You can actually do this just by knowing the topology of the solution. And what's interesting about this is that this is proportional to the entropy of these classes of black holes, of these static black holes and black strings. So from here we have some problem, some extremal problem where we extremize this subject to this constraint, which basically imposes the equations of motion, and this will give you exactly the dual of C extremization or I extremization. So Zaffaroni and Morteza, who's speaking tomorrow, showed that for type 2b, this is exactly dual to C extremization for these classes of theories. So a few comments about this. I want to really emphasize that these geometries arise as the near horizons of static black holes and black strings when it's ADS2 and ADS3. So let's just focus on the black holes for the moment, as this will be what the motivation for the paper. So there's two classes of ADS black holes. The first one is called magnetic ADS. And roughly, this is like, on the field theory side, this is like performing a topological twist. So these black holes can be static, but they can also rotate. And this is the class that is given by this I extremization, the geometric dual of I extremization, when they don't rotate. The second class are Kerr-Newman, which must always rotate, otherwise you get singularities and they're not supersymmetric. So for the GK geometries, which was the previous slide, only this first class we can get, and only when they don't rotate. So the natural question, and a question I was asked at any talks I gave on this, was what do you actually have to do if you want to account for the entropy of rotating black holes? So why isn't this covered in these works? So the rough idea is that for a rotating black hole, when you go to the near horizon, you may have some ADS factor, but what happens is that the internal manifold is also fibered over ADS. So when people generally do these SUSY classifications of supergravity, they basically assume that the ADS is not fibered over internal space. And so you'd never get these rotating black holes in these analyses. So a slightly less obvious fact is that if you were to look at 4D black hole and you add in electric charges, as soon as you uplift this to 11D, these electric charges get interpreted as vibrations over ADS. So also if you wanted to just try and add electric charges, you can't do this either. So just as a quick view, this is the general form of a black hole. So you see here, this is ADS2 here. And then you have these vibrations over the ADS2, where K here is a constant. And these are basically the fugacities of your angular momentum. So this is what we wanted to do. We wanted to look at how we could classify ADS2 solutions in 11D, allowing for all these arbitrary vibrations of this form here. So unfortunately, this form here is pretty unhelpful to try and do the SUSY analysis. So what you want to do is you want to rewrite this as something like dt plus a. So it's actually, you want to write it in something like this form here. And this, this motivates that you could use this classification of time-like structures in 11D by Jerome and Stathis in 2005, where they look at the geometry of preserving n equals 1 in 11D. You see that there's a killing vector in both cases. So there's a killing vector which can be either null or time-like. And if you take the time-like case, the metric takes this form here. So you have this time vibration, you have this vibration over this 10D space, and this is the, and then for what we want to do now, we want to basically give an ansatz for this 10D space. So the natural thing to do here is to look at what happens in the non-rotating case. So in that case, this 10D space is conformally a cone. So we just plug in the same thing. We plug this all into the equations of Galton-Packis, and we reduce this as far down as we can. So what happens is you end up with a metric of this form here. So here, the ADS2 is not very clearly written because it's written in some funny choice of coordinates, but roughly this part here and this part here will become ADS2 as soon as you take out this vibration here. So again, you find some R symmetry vector, which is the analog of the same in the non-rotating case. And here you have some 8D base. So rather than being Kähler in this case, it is in fact something a bit weaker, which is called a balanced manifold, which just means that dj to the n-1 is equal to 0 rather than dj equal to 0. And the two other new things are this scalar c here and this one form a here. But you can see if you set c to 0 and a to 0, this precisely gives you the previous GK geometries back. So as I said just before, the base is no longer Kähler, but balanced. And now you have a master equation, which is this very ugly mess here. So here, this is the Chern-Ricci scalar, which is equivalent to the Ricci scalar if it's Kähler, but if it's balanced, they're not equivalent. Then you have this Laplacian on this scalar C again, and then this is roughly the same term as before, R squared, and this is roughly the Ricci squared. And then a new part to this master equation, another new part, is that you have the norm of this four-form magnetic flux here. So you can see that if you set C equals 0 and H equals 0, you precisely get this formula back. So if you want to impose supersymmetry and have a solution, you need to solve this. And then there are a few extra constraints, which I've neglected to put in to save burning your eyes from painful expressions, that basically constrain parts of this magnetic flux. So everything is determined by this 8D, base and some primitive pieces of flux. So the final thing that we need to do is we need to impose SO2 isometry. So this isn't imposed by supersymmetry, this is something we want so that we can identify this with the near horizon of a black hole. So this imposes some additional constraints, and in particular it fixes the scalar C and the one form A in terms of quantities associated to the U1 killing vectors of the 9D space. And these are basically gives you a constant vector, which are dual to these fugacities of this angular momentum in 11D. Or if you look at it from a 4D picture, they're the angular momentum and the 4D electric charges. If you also impose that this base is something called toric, you can actually write these one form here in terms of nice geometric objects in this toric case. But due to time, I didn't bother. So the final thing we did was we gave an action for this basically setup. So this is one of the key things in how this C and I extremization geometric tool worked. It was that you could compute an on-shell SUSY action, which was proportional to the entropy of the black hole and string. And so we want to have something similar in this case. So I should warn you that before imposing supersymmetry, this is very ugly. It's this, which is 15 or 16 lines long and just not nice at all. But something very beautiful happens when you impose supersymmetry. you end up with just this tiny thing here. And this is precisely the same action as you had in the non-rotating case. So again, the entropy is given again by this very simple formula here, 1/4 g Newton times this on-shell action here. So this kind of says, okay, this extremization principle shouldn't be too hard to do, especially since this one is exactly the same. But unfortunately, there's bits that are a bit more difficult. So trying to impose the mass equation and flux quantization, and also to compute the angular momentum is a lot more difficult in this case. Roughly, you have terms of theorem which didn't appear before, and you can't just use the same formulas. But we can make a bit of progress if we assume some extra things, which are being Kähler, and if we also start switching off bits of flux that are just adding complications. So in particular, if you look at the, if you take these results, if you put it on a T2 and you do a reduction down to 2A and then T duality to 2B, you end up with ADS3 solutions, which are the near horizons of rotating black strings. And in these cases, this extremization is a lot more manageable. Okay, so I have 3 minutes, so I'm going to quickly conclude and give some outlook. So what we looked at was classifying the particular geometries of fibered ADS2 solutions in 11D supergravity. The motivation for this was to be able to essentially start to find a geometric dual for extremization for rotating black holes. So we have a generalization of these GK geometries to add it to the rotating case, which meant that we had to add in an extra scalar, an extra 1 form, and some 4 form pieces. And then this allows us to find near horizons of both rotating and electrically charged black holes. If we look at it from 4D, this is in some consistent truncation. Now, because we're not using these consistent truncations, this is quite nice because for large classes of theories, the most general truncations aren't known. So for example, if you just take YPQ, the most general truncation down to 5D is not known. But with these results here, we basically bypass this problem. So in the final minutes, what do we want to do now? Well, I think I've probably given the game away that we want to try and make this extremization problem, in this case, in the same way we did for the previous paper with Jerome, Dario, and James. And that the SUSY action is identical, kind of very tantalizing that it's going to work, but there's some problems still. A second question that I think is probably quite interesting is if you could actually try to incorporate high derivative corrections into this. So the first thing would be to turn off the rotation and then try to do it there. And then maybe this will also be able to give you some high derivative corrections and be able to compare with things by other people in the literature. They get some N subleading contributions. A second point would be that if you could do something similar for Euclidean saddles, so rather than, so these are basically width rotated black holes, and the near horizon is no longer ADS2, it's basically R2, or if you take a parameter, takes it to H2, then you can roughly width rotate and you get the black holes, these ADS4 black holes. And you should be able to do something similar. Thanks.
Okay, thank you, Chris. Thanks, Chris, for this very interesting talk. So, any questions?
I have a question.
Sure.
There was a paper called M Horizons by Papadopoulos where they had that. So is that too general? Why? It sounds a little quite a bit different from what you do. So I was wondering why. Is their answers too general or what? Do you
I
know?
think their ansatz is too general. They're more interested in the amount of supersymmetry you can preserve, as far as I remember. So they don't really get the they don't really understand the internal geometry, I think, from this perspective.
Yeah, they seem, yeah, that's exactly the reason I'm asking, because the conditions they get on the internal geometry seem a lot lax.
Yeah, I don't think they really reduced it as far as they could.
Right. Okay. I don't think they even have ADS2 for that matter. I mean, they are so general that.
Yeah.
Okay.
Any more questions? If not, let's thank Chris again. And Ioana, please share your screen. Okay. Ioana, can you make it full screen or is it?
If I make it full screen, then I don't see any more faces and reactions.
And you want to see the faces, okay.
Is it
yeah, it's
some
fine.
office like this?
I think it's fine. Okay,
right.
So we are very happy to have with us today Ioana Coman, who will tell us something about geometric description of topological string partition functions from quantum curves and integrability. Please take it.
Yes, thank you very much. And also thank you to all the organizers for the invitation and the chance to talk about some of my recent work. So I will give now a progress update on some work in collaboration with Jörg Teschner and Eli Pomoni from DESY, and also with Pietro Longhi from ETH regarding geometric description of topological string partition functions from the relation to quantum curves and integrability. So a reason to look at these is because topological string partition functions are ubiquitous, being objects of interest both in mathematics and in physics. They are on the one side related to various enumerative invariants, while on the other side, they are important in the study of gauge theories, where they can be used to calculate non-perturbative contributions from instantons to gauge theory partition functions. And they can be represented as an index that counts BPS states. Now, given the interest that they present, a number of approaches have been developed by now towards their computations. There exists the topological vertex, topological recursion, the holomorphic anomaly, and more recently, there was quite a lot of work on developing an approach related to spectral theory. Now, the perspective that I take looks at relations of the topological string partition functions, the Z-top, to quantum curves and integrability, with the aim to use these towards this geometric characterization of the Z-top. And I will explain to example how each of these, the quantum curves and the integrability, enter the story. So these examples are for the SU2 n equal to 2 gauge theories of class S, which can be realized through geometric engineering, starting from type 2b string theory on a local Calabi-Yau 3-manifold Y, where this is defined by an equation in terms of a degree 2 polynomial with a parameter x, which lives on a punctured Riemann surface C, and q of x, which is a meromorphic function. And I also will call this quadratic differential, having in mind that it is this quantity q of x d2x, which is the physically relevant object. Then generically q can be expanded as a sum over terms which characterize singularities. Here n is the number of punctures of the surface C, and the dots here are placeholders for possible terms with poles of order greater than 2. Now, if there are no such singularities, if there are no such higher order terms, the singularities are regular and otherwise they are irregular. So the examples in class S that I would refer to are the familiar pure SU2 superamials and SU2 for flavor theories, where in the first case, this C is a cylinder with 2 mildly irregular singularities, while for the SU2 for flavor theory, Q of X has 4 regular singularities. Then the curve determined by the vanishing of this polynomial is the Seiberg-Witten curve, and this labels a family of such Calabi-Yau threefolds whose complex structure moduli are then the parameters which enter the definition of the Seiberg-Witten curve, and which are, yes, the definition of sigma. Now, by mirror symmetry, the manifold Y is dual, related to a toric Calabi-Yau threefold X, whose geometry is encoded by a toric diagram, like this in the case of the pure SU2 superamials theory. The Keller moduli of X, which are associated to edges of the toric diagram, are periods of the canonical one form around appropriate cycles of the Seiberg-Witten curve, and they are related to the complex structure moduli. And then the topological string partition functions for such theories can be computed systematically, for example, using the topological vertex as a function of the Keller moduli and then a parameter h bar, which is related to the string coupling. So far, so good. But then in this context, an idea which goes back to the work of Dijkgraaf, Holland, Sokolsky, and Waffa, and which relies on predictions from string dualities, is to relate the z-top to a particular type of series expansion of a partition function for a system of free fermions, where the free fermions live on a quantization of the Seiberg-Witten curve. Now, this insight can be combined with an identification, which is done up to some proportionality factor of this free fermion partition function with the isomonodromic tau function. This is from more recent work of Gamayun, Yorgov, Lisovit, Teschner, and others. And where this is associated to a quantized Seiberg-Witten curve. Now, taken together, these two ingredients lead to a relation of the following type, where the tau function, seen now as a function of monodromy data mu associated to the quantum curve and expanded in appropriate parameters x, becomes a series, so a lattice sum, where the z-top enter with dependence on only half of these parameters x. And now what will emerge from the examples that I have mentioned and that I will discuss is that the quantum Seiberg-Witten curve is a key in the description of these z-top as analytic objects by determining here the normalization factors and the parameters x, which allow to identify these two sides. Now, ultimately, what I want to convey with this is a geometric description of the topological string partition functions as sections of a line bundle over the moduli space of quantum Seiberg-Witten curves. And to make this idea precise, I will start with the relation between tau functions and z-top. So here on the one side, we have to determine what is meant by a quantization of the Seiberg-Witten curve. And the answer here will be to describe this as a D module and to allow for quantum corrections, whereby the tau function will then describe the isomonodromic deformations of this D module. The second point is then to find the good parameters for the monodromic data which is associated to the D module, in which to expand the tau function in order to relate the resulting functions on the right-hand side to the z-top. And it is this part of the story which has turned out to be quite involved and requiring a series of papers to explore it. But having all of this, Then on the other side, we of course need to compare wherever this is possible with results for the topological string partition functions derived via a well-established method. And here I use the vertex. So let us turn to the quantum curves from the perspective of integrability. So the Sabag curve becomes quantized by making the parameters x and y non-commutative. By replacing y with a differential operator, the quantum curve can be described, like I said, as a D module, which now captures solutions to such second-order linear differential equations, where the classical function q of x is now allowed to receive quantum corrections. Now, this formulation can be equivalently recast in terms of a connection with a flat section psi of a vector bundle on the curve C, where psi contains the solutions to this differential equation. And in local coordinates, this connection can be expressed as an upper, which has only off-diagonal non-zero entries. Now, viewing the quantum curve in this way is useful towards determining what exactly the quantum H bar corrections here are, and also to set up the problem in such a way that the monodromy data characterizing this equation is sufficiently general. So now, considering a generic connection matrix with non-trivial entries everywhere, this can be brought to upper form by a singular gauge transformation, which gives the deformed q of x. Now, this part is the original function, and to see explicitly these corrections, we can look at a quadratic differential on a punctured Riemann surface, which has only regular singular points. So irregular singularities can be created from these in a confluence limit by colliding regular singular points. Now, the gauge transformation that I mentioned earlier transforms the H bar connection into an upper with apparent singularities, or equivalently a quadratic differential of this type with new parameters V and U at order H bar. Now, these new singularities are called apparent because they are an artifact of the procedure of the gauge transformation. And furthermore, to be written in this form, this equation comes together with constraints for the newly introduced parameters, which together with the regularity of the quadratic differential at infinity give a number of equations for the H, which is equal to the number of punctures. Now, here is where this approach to quantization differs from what people might usually have in mind when thinking about this, in that it is more than simply making the classical coordinates x and y non-commutative, but rather by allowing for these apparent singularities and by introducing these extra parameters, it is possible to then account for general monodromies. Now, I mentioned the set of constraints. This is in fact sufficient to determine these functions h, which appear in QH bar, as functions of u and v, and then variations of the h with u or v are related to variations of these guys with respect to the positions z of the punctures on the base curve C. And now, given such relations, as the punctures move on C, the monodromies, which encode how the solutions to the quantum curve equation transform under parallel transport on C, that means this monodromy data, this remains unchanged. So then, therefore, these H are the Hamiltonians, which generate isomonodromic deformations, and then they are, by definition, themselves generated by the isomonodromic tau function here. Now, I should remark that these equations, they define a tau function only up to multiplication by another function, which is independent of dz. So they leave, in fact, some freedom in the precise normalization here, which I mentioned was important. Now, particular I should say that the tau functions for the cases of interest that I mentioned, so the pure SU2 spiral theories and the SU2 for flavor theory, this can be found in many places in literature. And particularly useful references here are these two, a main result of which is the existence of theta series expansions for these tau functions. And furthermore, already in these references, the authors comment on a relation between the isomonodromic tau functions and Nekrasov-Vincenton partition functions. So it stands to reason that these should be furthermore related to topological strings partition functions. So far I've paved the route to discussing about the tau functions, setting aside for now the quantization of the curves, and returning now to the original aim. We now need to focus on this point to find good parameters for the monodromy data, that is, pairs of coordinates separated by a choice of polarization, which allow to write a theta series expansion for the tau function. Now, before building to a general description of how to systematically determine good coordinates, it is useful to start by looking at certain possible parametrizations for the monodromy data. So now the solution to the differential equation which quantizes the Sabag-Witten curve, this is analytic on the curve sigma, so on the Sabag-Witten curve, but acquires a monodromy when continued around such paths gamma on the base curve C, where these enclose punctures. So the space of monodromy data that I was mentioning earlier is the corresponding character variety, whose algebraic structure is expressed using trace functions of holonomies around the loops gamma, like this one, considering the parameters which are associated to the punctures to be fixed external inputs. So in the case where, like you see here, C is a 4-puncture sphere, the character variety is parameterized by 2 coordinates. And there is these various possible parameterizations in terms of what are known as Foucault-Struve or Fenchenius coordinates, and I will explain a bit more what these are. But the property that I want to highlight for now is that these provide rational parameterizations of the trace functions. Now, these guys, the Fenchenius type coordinates, are special. They are associated to spectral networks like depicted in black here on these 3 puncture spheres. So these spectral networks, they are graphs on the base curve C, which are formed by walls which are defined by the quadratic differential. Now 3 walls emerge from each branch point of the quadratic differential, and then each wall is formed by points x, which satisfy a constraint on the integral of the Sabag-Witten 1 form going from 0 to the point x. And in the case of Fenchenius networks, these walls connect only pairs of branch points. So the networks decompose the surface C into a set of annuli and puncture disks. So they therefore define a pair of paths decomposition, like you see here, when on each resulting 3-puncture sphere, the molecules look like one of the graphs that I have depicted here. So for example, on a 4-puncture sphere, such a Fenchenius network can be formed by 2 such molecules. Again, they are depicted in black, where the molecules sit each sits on a pair of pants on a 3-puncture sphere, and the 2 are glued along a distinguished boundary. Now here, by a procedure called abelianization, it is possible to explicitly construct the monodromy matrices and consequently the trace functions, which get parameterized in this case by the external data, so the theta I associated to matrices giving the holonomies around the punctures, and 2 coordinates, sigma and eta, which are associated to the monodromy around the distinguished boundary where the 2 3-puncture spheres are glued, and to the parallel transport, which is across the connecting cylinder. Now, by adopting this point of view to decompose a surface into building blocks, what emerges is a relation between such coordinates and normalizations of these solutions chi to the differential equation. Now, this parameterization that I've outlined here, what we found is that it can be used to expand a normalized version of the tau function, which is computed here for the Pan-Levé-Stix equation. It is taken from this reference, such that the expansion is a generalized theta series of the type that we wanted, with the parameter eta from the previous slide entering the exponential prefactor, and then sigma enters the argument of a function with lattice shifts. And this function, I have verified, matches the 4D limit of the topological string partition function calculated for the SU2 4-flavor super Yang-Mills theory using the topological vertex and applied in this case to the octagon toric diagram that I have depicted here. Now recall that such toric diagrams encode the geometry of the toric Calabi-Yau threefold X, which is mirror dual to the local Calabi-Yau threefold Y that entered the geometric engineering, in this case of the SU2 4-flavor theory. So what this means is that this Z top belongs to a chamber in the extended Kähler moduli space of parameters of the manifold X. And already finding this agreement was very comforting because it was very non-trivial confirmation of the predictions from the older papers. But we did even better because on this side, it is easy to calculate these Z-top functions in other chambers of this extended Kähler moduli space of parameters. So what I mean by this is it is possible to calculate these functions for other toric diagrams, which are related to the octagon by flops. So this is referring to a local change in the way in which the edges of the toric diagram are connected. And where these other diagrams also correspond to manifolds which are mirror dual to the same local Calabi-Yau threefold Y. So now what we found is were systematic transformations matching each possible configuration of Fencher-Nielsen molecules with its corresponding coordinates for the monodromy data to an appropriately normalized tau function, which admits a generalized theta series expansion in these parameters. And these expansions then generate topological string partition functions in the different chambers of the extended Kähler moduli space of parameters for X. And this is good, but it is not quite satisfactory because what I have shown up to now is that it is possible to extract these Z-top from corresponding normalized tau functions using only very particular coordinates on the character variety. So those determined by Fencher-Nielsen networks and abelianization from very particular quadratic differentials. Now I'm saying that these spectral networks are very special because by contrast, those networks defined by generic quadratic differentials are composed of walls that connect poles of the quadratic differential to its zeros, and they determine a triangulation of the base curve C, as opposed to a pair of pans decomposition like in the Fencher-Nielsen case. And then to such triangulations, it is possible to associate for control coordinates, which also determine parameterization of the character variety. And then in between the two extremes, there exist mixed networks, which will have some number of saddle trajectories and corresponding hybrid type coordinates. But now back to the original goal to construct a geometric picture for the topological strings partition function as sections of a line bundle over the moduli space of quantum curves. For this to be possible, we must be able to use such tau functions appropriately normalized on patches of this space as the objects from which to extract the corresponding z-top functions from theta series expansions, but for general parameterizations of the character variety. And then covering this space by coordinate charts, changes of coordinates on overlapping patches should get matches to changes of normalizations for the tau functions, like we saw in the case where we had Venturi-Nilsson coordinates. So how to associate such distinguished coordinates to different regions on the space of quantum curves, but starting from the quadratic differential, which specifies the Seiberg-Witten curve. Well, on the one hand, we saw that the quadratic differential determines a spectral network on the base curve C, while on the other hand, its quantization leads to a differential equation whose solutions can be studied using exact WKB analysis as formal series expansions in this deformation parameter H bar. Now, such solutions normalized at a certain point on C, here this is a nodal point of the spectral network. These can be constructed using a set of recursion relations which determine a formal series here, S, as solutions to the associated Riccati equation. Now, these solutions then satisfy certain analytic properties under continuation across Stokes curves, that is the walls of the spectral network, and they can be Borel summed away from these curves. Now, this formal series S, or should I say this one, can also be used to define what are called Vorosh symbols associated to particular loops on the curve C. And this has been shown to be Borel summable when the spectral network is generic. That means that it is formed only of walls that connect branch points of the quadratic differential to the punctures of C. And in such cases, the Vorosh symbols have been recently identified with Vogontsov coordinates on the character variety associated to triangulations which are dual to these generic spectral networks. Now, there is furthermore a relation between ratios of exact WKB solutions and Vorosh symbol, which then determine the normalization factor, or other factors, relevant for our purposes when studying normalizations of the tau functions. So exact WKB analysis is a tool which provides both normalizations of the tau functions and allows to define coordinates in terms of which these normalized tau functions can be expanded to produce generalized theta series. So this might be a bit abstract, but I can show what this actually means in a few examples from which there will be two main messages. So one will be that the space of quantum curves that I was discussing cannot be parameterized using only one type of coordinate. And furthermore, that the Vogontsov and Venturi-Nilsson coordinates turn out to be related. So looking now at the example of the pure SU2 super-Yang-Mills theory, here the base curve C is a cylinder with two irregular singularities at the punctures of 0 and infinity. The associated tau function is that of the Pan-Levet-Rie equation, and this has been shown to admit generalized theta series expansions in different coordinates. And I have calculated on this side that what we find here, circled in blue, is the topological string partition function Z top calculated using the topological vertex and this box toric diagram. We can also identify the coordinates on this side to be of Venturi-Nilsson type. And this is because here the monodromy matrices, which are associated to paths around the cylinder and also connecting the two punctures, can be simultaneously diagonalized for an appropriate basis of flat sections for the connection. And then on the other side, we identify these coordinates to be of Vogontsov type. And the two pairs are related by a simple transformation. Now, how to see this point, this property? Now, here is a general full-control spectral network on the cylinder. It has no saddle trajectories and determines a triangulation depicted here in gray of the surface, the edges of which have associated full-control coordinates, which are related simply by exponentiation to the ones I had previously. Now, performing a flip on this triangulation and subsequent relabeling, which generates a Dane twist, or just a rotation of the cylinder, the Fogg-Gonchar coordinates undergo a particular transformation. Now, under reparametrization to now exponential versions of the sigma and eta of the Fenton-Newton coordinates, this map now takes a much more simple form. And then repeating the sequence of flips an infinite number of times can be seen to have a small effect on the Fenton-Newton coordinates. It will, however, have a significant effect on the Fogg-Gonchar type. And this allows to see how the Fenton-Newton coordinates in fact arise as limits of the Fogg-Gonchar coordinates. So from this one example, to reiterate, the takeaway message is that it is both types of coordinates are needed in order to study theta series expansions of the tau functions, and that the two types of coordinates are closely related. So now an immediate question is whether the same relation holds elsewhere. And here there is the answer is yes. We see this one revisiting the SU24 flavor theory by looking at the trace functions for such loops, both in Fogg-Gonchar and Fenton-Newton coordinates. So when going from the cylinder to the four-puncture sphere, there exists a Fenton-Newton network here, which determines a pair-pans decomposition, and which on the connecting tube looks the same as its counterpart on the cylinder. And then the dual networks are both generic and also resemble each other in the same region on the connecting cylinder. Now, the same transformation as before maps the Fenton-Newton coordinates determined by this network to the Fogg-Gonchar coordinates associated with the dual triangulation on the other side. And the traces L gamma, for here in red, they agree since in both cases they coincide. But what was very reassuring was to find this agreement to hold more generally for functions which have much more complicated expressions. So now we can draw some lessons. What we find as the emerging big picture is that the moduli space of quantum curves is equivalent to the moduli space of H-bar deformed connections on the base curve C. That is the space of triples given by a complex parameter H-bar, a holomorphic vector bundle on the base curve, and a flat connection considered up to equivalence under gauge transformations. And then by a series of projections, it is possible to go from this space to the Hitchin moduli space by forgetting the H-bar here and identifying the connection matrix with H-bar set to 0 with the Higgs field. And then from here, since the Hitchin moduli space can be seen as a torus vibration, there is a further projection to the base, which takes the Higgs field to the quadratic differential that defines the Sabag curve. And then on the base for the Hitchin vibration, possible coordinates are the homological ones, which are defined by period integrals of the Sabag curve of the Sabag differential on a basis of loops for the first homology of the Sabag curve. Now the space set calligraphic, the space of quantum curves, this admits a covering in terms of patches with Darboux coordinates on these patches obtained from the holonomy map, which takes points on the set to points on the corresponding character variety. And then an important feature of these coordinates is their asymptotic behavior as H-bar goes to 0 and the relation to the homological coordinates. So then on these patches, appropriately normalized tau functions can be seen as distinguished local sections of a line bundle on the space of quantum curves, which admit such generalized theta series expansions in the corresponding coordinates x, and whose expansions then gives the topological strings partition functions. And then by adopting this point of view, what we see is, and what we have seen is how changes of coordinates between patches on Z calligraphic translate to changes of normalization for the tau functions, which therefore represent transition functions for the line bundle. Now, instead of projection to M Hitchin, we can stay at a fixed point here and project onto C star. And we can look at how the spectral network for a given fixed quadratic differential changes as this H bar parameter is allowed to vary, which only changes the overall phase of the spectral network. So then this place can be seen as a union of wedges separated by a trace. To each wedge corresponds then a generic spectral network, which then changes, which has a given topology and which changes when going from one wedge to any of the adjoining ones, and whose Fogonchev coordinates are related by cluster transformations. And what we have seen from the example of the cylinder is that the set of angles defining the rays may have accumulation points where the rays get close together and the topology of the network changes by an infinite sequence of flips. So then it's natural to associate Fenchel-Nielsen coordinates to these accumulation rays. So I'm close to finishing. I will just say that this matters because the collection of cluster transformations which relate the sets of Fogonchev coordinates. This can be seen separately as input data into Riemann-Hilbert type problems which characterize these coordinates. And these are been relevant in recent work on BPS structures by Tom Bridgeland, and also in relation of these to topological recursion and exact WKB analysis. And what we see here is that it is important to incorporate into this Riemann-Hilbert problem, also into the solution, also the data that comes from the other types of coordinates, so the Fenchel-Nielsen ones and possibly the mixed ones. And because otherwise there would be no way to assign topological strings partition functions to the neighborhoods on the moduli space of quantum curves, which are associated to Fenchel-Nielsen spectral networks. And these are important because they admit in relation to topological string theory because they admit weakly coupled expansions. So now I come to the outlook part, and I'm very low on time, so I will just say that there are clear directions in which to expand this, also going to higher genus or higher rank, or going up in dimensions, because now we're in 4D, and we could look at the 5D counterpart of this story, where for example, the Pain-Levé equations become Q different Pain-Levé equations, and where the spectral networks have more complicated behavior. And we can also explore the relation to the other lines of research.
Thank you very much. Let's thank Ioana for the talk. So we have time for one question before we go to a break. So are there any questions? So let me ask about going to higher rank. How hard it is you expect to be?
Well, I was talking with Kohei Vaki, one of the researchers I cited. On the side of the WKB analysis, things become more complicated. On the side of spectral networks, when we already know from the large body of work of Guyot, Tomura, and Naitsky how much more complicated the spectral networks become there as well. And there is more complicated phenomena appearing. So I tried to keep it light and gloss over the big technicalities that can arise already with rank 1 theories, because when actually getting this identification with really having an equal sign between the tau function with this normalization and the z top, we have to figure out many ambiguities as to where to normalize, how to continue as things move. So yeah, all of this gets multiplied when going to higher rank.
But you think it's doable?
Yeah, absolutely. So there are many results that exist, both on the side of the tau functions and knowing the BPS spectrum and structures. So
Thank you.
Can I have, ask a question now?
yeah.
Yes.
Yeah, I just want so how concerning these exponential networks. So so here I wonder how generalized that for the torical Calabi-Yau, that this partition function can also relate to this tau function of this integrable system.
So here I haven't looked that much into. There is some work by let me see, Pavlo Gavrilenko and his collaborators. So they have looked on the side of the integrable systems at the Q-deformed versions of the Panevet equations and calculating the tau functions. Now, I just remember from a talk by Pietro Longhi from last year, where he was exploring this 5D uplift of the spectral network and the new structures that appear that are not visible when we're in 4D. Yeah, it would be very interesting to answer this question on how the two are related, how to see the connections, but I don't have anything terribly illuminating to say at this point.
Okay, thanks.
Okay. Thank you very much, Ioana. Let's thank Ioana again and all the speakers of the first session for very interesting talks. So I will now stop the recording. We will keep the Zoom channel open, and we will meet again in 25 minutes or so. So the next session will begin at 2 p.m. Eastern Time or 7 p.m. GMT, and we'll have Simone Giacomelli, Pietro Benetti Giannolini, and Jinxian Wu in the next session. So see you all very soon. So I'm stopping the recording. So if you want to say crazy things and discuss more freely, you are welcome to do it now.